Hi, everybody. I'm Gaurav Deshpande, Vice President of Marketing with TigerGraph. Welcome. Thank you for taking the time out of your busy day to chat with us. Today's topic is GSQL writing best practices. This is the third part of that particular series, and this one is focused on memory optimization. Let's go to the next chart. Shinu, if you can go to the next chart. Perfect. A little bit of an introduction about myself. I lead all things at marketing for TigerGraph. If you have any questions about any of our offerings, feel free to contact me. The way to contact me is very simple, Gaurav, my first name, at tigergraph.com. I have done multiple startups, the last two startups that I did, a little bit of information about that. Started my graph journey really back in 2009 and started learning about it. Been doing graph for about 11 years. Love to know more. I would love to connect up with you on LinkedIn, and so will Shinyu. So feel free to send us a LinkedIn invite after this call. With that, let me actually introduce you, the man of the hour, Shinyu Chung. Shinyu, would you like to introduce yourself briefly? And then I can go into some housekeeping items before we jump into the presentation.
Okay. So hi, everyone. I'm Xinyu Cheng. So I'm the Director of Customer Solutions. So I worked in the language team for about 2 years. So I implemented a lot of GSQL features. So I really know the language inside out. And I also develop solutions for a lot of very big customers, Fortune 50 companies. And I have been with with TigerGraph for over 5 years, almost 6 years. So nice to meet you guys.
Excellent. Some housekeeping items before we jump into the meat of the presentation with Shinyu. There is bottom right-hand side of the Zoom screen, you'll find Q&A. If you have any questions, feel free to click on Q&A and tee up your question as we are going through. A lot of times people wait till the end of the presentation. You don't need to. You can keep on asking questions, and we will cover all of your questions at the end of the presentation. The webinars are being recorded, and they will be available at tigergraph.com/webinars. We will send you a URL after this particular, if you have registered for it. And anytime you want to check out, for example, the part 1 or the part 2 of this GSQL writing series, or about any other webinars, you can go to tigergraph.com/webinars, visit that to get that information. Of course, if you have any issues with Zoom, please contact the panelist via chat, which you will see right in the middle of your Zoom panel. And with that, let me hand it off to Shinyu to cover the matter today.
Okay, thank you, Gaurav. So today we are going to do the third episode of query writing best practice, that is the memory optimization. In the previous 2 episodes, we talked about the ways of designing the most optimal traversal path, as well as what to think when we write GSQL queries, like where do we start from, and what are the factors that we need to put into consideration when we start to write a query, okay? And if you are interested, you can find those videos from our YouTube website. So hopefully those will be very helpful to you. And today we are going to talk about memory optimization. This is a very important topic when we write the queries, because as we all know, like a TigerGraph is a in-memory graph database. Everything is performed within the is in memory, right? The data storage is in memory, and the query also runs in the memory. So how to manage the memory wisely is very, very important if you want to write scalable and performant queries. Okay, so in today's talk, I will cover 4 topics. The first one, I will talk about the memory composition of TigerGraph system. And then I'll talk about how to check and monitor the memory usage. And next, I will talk about what are the operations or query semantics that can result in very large memory consumption. And at last, I will talk about the techniques to optimize the memory usage. What to do if your query really consumes a lot of memory? Well, what can we do to mitigate this situation? Right? Okay, then now let's start with the memory composition of TigerGraph. So by looking at the chart, you can see the memory composition of TigerGraph system. On the right-hand side, the large rectangle, this is your system memory. So if you have TigerGraph installed in your server, so most likely the memory composition will be look like this. So in usual case, the GPE graph processor engine and the GSE graph storage engine will take the most of your memory because GPE and GSE, they are the size of memory consumption from these two components, they are proportional to your input data. That means the more data you load into the system, the larger size of GPE and GSE you will get in the memory. Okay, so here the GPE majorly stores the graph partitions. By graph partitions, I mean the vertices and the edges in the internal format. Since everything is stored in the internal format, that means the IDs are also in the internal format. We store the data vertex ID in the integer type internal ID format. That means we need another component to translate so that we can communicate from outside world. For example, you take a user ID as an input to a query, then we will need GSE to translate it into internal format so that GPE can process, can find it from graph and do the graph reversal. So GPE stores all the vertices and the edges, and GSE is a bidirectional ID mapping, maps from the external ID, which is the original string ID, to the internal format integer ID. That's GSE. Okay, and also we have some other components that is pretty trivial. They are not proportional to the data size. So usually when we think about memory, we majorly take these two into our consideration. Okay, and then let's further look at the GPE. So for GPE, a graph update will also take a large portion of GPE's memory consumption. For example, if you have a system that frequently does a real-time graph update, and all the new update will store in a location so that they can be queried or accessed, right? So it takes some memory to store the new data, newly updated part of the graph. And then beyond that, every query will have its own like a memory space. That means the more query you run, the larger memory consumption you will get from GPE. Okay, and also for the more memory consumed by each single query, the more memory will consumed by GPE as well, because each query is a part of GPE memory consumption. And then now let's take a deeper look at the memory composition of the query on the left-hand side. The rectangle on the left-hand side is the query memory, okay? So when we run the query, we all know we can define the global accumulators and the local accumulators. Actually, that's the part that consumes the most memory. That is the most memory consuming part from a query. Someone may have a question, okay, if I have a query, it traverses billions of edges. Does that take a lot of memory? The answer is it doesn't actually. So because as we all know, each vertex and each edge is a computational unit. So we don't have to replicate into the query memory again. You can directly run the query on the vertex and edges. So if you traverse a large amount of vertex and edges, that doesn't consume actual memory. However, defining very large global accumulators and the local accumulators, that consumes a lot of memory. And other than the accumulators, another thing is very significant is the shuffled partitions and accumulators. That is when we run the query in the distributed mode, sometimes we don't have all the information in one server, right? Sometimes we need to transfer some either graph partition, vertex attribute, or accumulators from other server. So that will require you to spend more memory on this shuffled data. We need a location to store them in order to use them in the calculation. Okay, so other than that, these are the insignificant items. For example, the activated vertex set or upserted vertex and edges. These only have a very limited memory usage. So this is the memory composition of TigerGraph. So next, I will talk about how to check and monitor the memory usage. So there are 4 ways of looking at the memory consumption. I'll go over each of them. So first, for first method, you can do it from command line. You can use run command, min status -v graph. This is a very commonly used command. With this command, we can quickly check the total vertex count, like this, and the total edge count, as well as the partition size and the IDS size. So these 2 numbers are corresponding to the GPE size and the GSE size. As we all know, the GSE is a bidirectional ID mapping, right? And the GPE stores the graph partitions. So this means the partition size of GPE is 72 gig, while the ID service GSE size is 28 gig. So that means by combining this number is the size as the memory is the size of your memory consumption of your graph. That means if you run the TigerGraph system and when it stays idle, each server will consume about 100 gigabyte of memory when it's idle. Okay, and you can also check the memory consumption on each server with this command. This is how we do it from command line. And also, we can easily check it from our UI. So if you open the Graph Studio, on the right top corner, you can see a button that says admin. So if you click into it, you can look at the system monitoring dashboard. And one of the chart here is the memory monitoring. You can look at here, okay, for GPE, it consumed about 78 or something memory, and for GSE, consumed about 28 something memory, and the total is around 100. Okay, this is another way of checking the memory. That is from the Graph Studio UI. And the third way is you can check it from the logs. So there is a log called log.info of GPE log. So you can find the location of your log info of GPE log by running command geodamin log. That will list all the logs, and you can easily find the log.info GPE log. So log.info log is a daily log of GPE. Everything normal will be printed there. So one of the lines in the log you will definitely see in the log, because this line is printed periodically every few seconds, right? So it prints this memory consumption of your GPE component. So let's take a deeper look at this line of log, okay? So first thing, we can see the current memory consumption called current GB 78. So that means the currently GPE consumes 78 gigabyte of memory, and then followed by 2 system settings. These are not monitoring data. These are the system settings. So let me explain this to you. So system mean free percentage 10. This means when the system has less than 10% of free memory, it enters a system critical state, memory critical state. So if the system enters the memory critical state, it will start to abort all the running queries, and the new queries will be aborted too to prevent the system from crashing. Okay, and the next configuration is system alert free percentage. So the first configuration is for the limit for critical state. And this 30% means is configuration for alert state. That means when the system has less than 30% of free memory, it enters alert state, and the alert state will slow down the graph update, so that the memory increase of the GPE component will be slowed down in that case. So the last one is the percentage, the free memory percentage of the system. So if it's 87, means system has 87% of free memory. So this is how we check it from the log of GPE log. We can check the memory consumption from there. And the last thing, the last method is we can also get the GPE memory consumption status by calling this endpoint. So this is actually the endpoint of TS3 component. The TS3 component is the component that provides the dashboard of the monitoring dashboard. Actually, this result is obtained by calling this RESTful endpoint. Okay, so if we call this endpoint with a start date, start epoch time, and end epoch time, and also here we specify I want to check the GPE on the first node, the memory consumption of GPE on the first node, then you will get a JSON response like this. So the result is pretty straightforward. It says, okay, for the GPE on the first node, the memory consumption is 77 gig, it's in megabyte, okay, and the time point, so that you can easily visualize a line chart or bar chart with all this info, because it shows the historical memory consumption of your GPE in different time point. I think the frequency is hopefully like a once per minute. Okay, so these are the 4 methods that we can either check or monitor the memory usage of GPE. Okay, so now we know how to monitor and check the memory consumptions. Then we want to find out what query semantics are most memory consuming. That means when we write
I see that some of the people have started adding questions already, but if you have a question, just click on the Q&A at the bottom and then start to add questions there, please, as we go along, and we will address all of your questions at the end. Thank you. Sorry, go ahead, Shenyu.
Okay, thank you. So, so in this session, I want to talk about when we write the queries, what's query semantics we should be really careful about, right? Like so because they are very memory consuming. So these are the query semantics. First thing is container type vertex attached accumulators. So vertex attached accumulators are those accumulators defined starting with a single @ sign, because we know global accumulators they start with 2 @ signs, right? So that means if we define an accumulator with a single @ sign, that means it's defined on every each vertex participates the query's traversal. Especially when we define a container type accumulator as a vertex type accumulator, that means we are defining a container on every each vertex participates the traversal. So if we traverse hundreds of millions of vertices in our algorithm, then you define the map as local accumulator. That means you have defined the hundreds of millions of maps in the memory. That's a large memory consumption. Especially you start to populate elements to that map. That's a very, very big. Okay, so that's the first thing. And the second thing is sometimes the global accumulators can be very large as well. Like we define the map has billions of key value pairs. Then hopefully 100 gigabytes of memory will be consumed in that case. So we also should be very careful about that. So here, by container type accumulator, I have listed all of them down here. They can be set accum, bag accum, I did again, sorry. List accum, map accum, heap accum, array accum, and group by accum. right? All of these are container types, and the container type consumes more memory than the primitive types, especially you define them on every each vertex. It's very, very memory consuming. Okay, and especially I actually mentioned it in previous slides that the major memory consumption from a query are accumulators. So we should really be careful when we design the algorithm and when we define the accumulators. And the third thing is the attribute and the accumulators on the target vertex. So this only applies to when you this only applies when you have a distributed system. The reason is, let me do some whiteboarding here. Stop share and share a whiteboard. Okay, let's do some whiteboarding here. Say if we have two TigerGraph servers, this is server 1 and this server 2. And on server 1, we have vertex A, and along with all the neighbors of vertex A. And in another location, we store the attribute of vertex A. So far, we are all good. We use the neighbors, we traverse the edges, get the attribute from vertex A, we are all good. But in another server, it stores vertex B and the attribute of the vertex B, right? And now vertex B is a neighbor of vertex A. And then we write a query, say, okay, I traverse from A to B, and I want to put B's attribute into a filtering condition. I want to say, hey, if where B dot attribute equals to something, right? In this case, if the server 1 is running processing the query, and it want to use attribute vertex B, that means we need to shuffle B's info to server 1 in order to finish the computation. And all the shuffled vertex to server 1 will take actual memories and also need to consume some network resource in order to transfer the data over. Okay, so in this case, utilizing, accessing the target attribute, target B here, B is the target vertex to A, right? So accessing the attribute or accumulator value of your target vertex will take up actual memories. So in this case, to mitigate this problem, we can consider to apply this filtering in having clause. If you run this query distributed, having clause will be performed right here without having to transfer the data over. Okay. Okay, let's come back to the slides. And here I'm going to talk about, I just talk about what operations are memory consuming. And now I'm going to talk about the techniques to optimize memory usage. What are the solutions, right? Okay, so the first question is, the first technique is we can define light-weighted accumulators. So this is the use case based on one of the largest payment and financial service company in the world, right? So when they do anti-fraud, they would extract all the paths from the graph and then evaluate the passes and then give assign a score for each pass, and then they use the score as a feature of the anti-fraud use case. Okay, so basically what it does is it defines a pass, list of list. That means by list of list, it means each list in the big list is a pass, right? It's a list of string, so we store type in it. So it will be something like this. Say type A, type B, type A, type C. That's the content of each list we are going to populate, right? So we have, in the same way, because it's a list of lists, we will have multiple lists in the big list, right? So, okay, so in this case, this is the data structure we defined, and this is a complex data structure that is a local accumulator. That is means for every vertex we have traversed, we will have this structure defined there, right? Okay. Okay, so that is very, we know that this is very, very expensive, right? For example, what this query does is it starts from an input, and with a while loop, it just traverse layer after layer, and it populates the passes along the way. And in the end, we print the result out so that we can analyze a score from the returned passes, right? So that we know this is a very memory consuming, because think about it. If we start from an input vertex and it traverses hop after hop, and if after we have traversed very far away, the list stored on the vertex will become longer and longer, right? Like this one will store a pass, say AB, and this guy will store ABC. And the further what the vertex is from the start, the longer the list become, especially when we have multiple passes like this, right? Then the number of passes can be very, we can have multiple passes on one vertex, and each pass may have a lot of elements. So in the end, you will look at on every vertex, we will have a very big data structure like this. Something like this. We have many of these on every each vertex. Okay, so alternately, so in this case, we want to in order to optimize the memory consumption, what we want to do is we can, hey, because ultimately we just want to have a score. That is all we want. Do we necessarily carry around the pass in order to calculate the score? The answer is no, not necessarily. We can actually optimize this query by defining only a float type sum accum on every each vertex. Because we know the type of the vertices we're going to traverse. And in the same way, we can translate the query from the previous slides to a query that only have the sum accum of float defined here. So this way we can convert a lot algorithm like this, right? If this score of this guy is 0.5, then this is a 0.7. And then we can say, hey, this guy is 1.2, right? And if this guy is has score 1.3, then we just multiply the numbers and then follow the same pattern to traverse to the next layer. Then in this way, in the end, we will get the exactly same ultimate score, but we are using a way more lightweight data structure. It's a lot more memory saving and a lot more faster than the previous algorithm. So this is actually based on the real use case. Okay, that's the first technique, is to think about, can we define the more lightweighted accumulators in order to, and we can also get the same result. Okay, that's the first technique. And the second one is, for some of the algorithms, we can split the query load into batches. So when is this needed? When, first thing, the query involves all or significant fraction of all vertices, a large number of vertices participate your calculation, right? And also each hop accumulates a significant amount of data in every local accumulator or in the global accumulators. Okay, now let's look at the example. Okay, so now this example is, for each company, find the majority type of subsidiaries. So assume for each subsidiary company, it has a type. And we want to ask a question like, for all the companies there is in the world, what is the majority type of subsidiaries? That means, let me give you an example. For a company A, it has a list of subsidiaries. We have many, many of those. And say the subsidiary 1 is under type A, subsidiary 2 under type B, and subsidiary 3 is under type A again, and the subsidiary 4 under type D. Then A is a majority subsidiary because we have two A's. We have two subsidiaries under type A, one under B and one under D, right? So the result should be A. But in order to calculate this, we need the help of a map because we need to aggregate all this info to the vertex so that we can construct a map. Say, okay, I have A as a key and I have two A's. We have one B and one D. Right? That's what again what we're gonna do. So in this case, if we do this for all the companies, then that means in parallel, all the companies will start to construct their own map, and that's a big map, and every company will have that. Right? That's a lot of memory. If you have like 10 billion or 100 billions of companies in the world, then that's 100 billion maps with all kinds of this aggregated info. That's very memory consuming. So alternately here, we can, this is the intuitive way of writing. No, this is the example how we split the workload, right? So we can divide those 100 million companies into 10 batches so that each time you only do the calculation for 10 million companies. This way, only 10 million companies will populate this map structure, and then we clear them out in the end. So hopefully we only use 1/10 of the memory as before. How to do that? So it's very simple. So all you need to do is just follow these semantics. So we can take an input k. K means I want to split the query into k batches. And we can split the batch with a for each clause, traverse from 0 to k minus 1. And every time from all companies, I select those internal ID mode by k, and the number is I. I is the iterator of this range, right? So every time you select exactly, if k is 10, then every time you select exactly 1/10 of the vertices to perform this calculation, and in the end you clear the map out so that it releases the memory. Okay, so the basic idea is if everyone does a memory consuming operation is very, very memory consuming, then we can just pick a subset of the vertices to do it first, and then we clear out the data structure and go to the next batch. So this will be memory saving as well. Okay, and this technique is also can be used for graph algorithms such as label propagation or Low-ins, which are widely used by bank customers. They use that for anti-fraud and something like that. Okay, so that's the second technique. And third one is query calling query. So query calling query is memory consuming, consumes less memory because we have moved we have split the very heavy workload into split it into multiple subqueries, right? So when is this needed? When we start from a larger amount of vertices, and the result for each starting vertex needs to be collected from a subgraph in more than one hops. Okay, so breaking a query into subqueries usually results in simpler data structures, therefore consumes less memory. And also, only a limited amount of subqueries can be run in parallel. That's one of the mechanisms of TigerGraph system. If you do query calling query, and from accum or post-accum clause, then only very limited amount of subqueries can be run in parallel. And then memory is recycled after a subquery is done. Okay, now let me give an example here. So for example, in the enterprise graph, we want to find the companies having more than n subsidiaries within k hops that went out of business. Okay, so this is the intuitive way of writing this query. We start from all enterprises and we find those who has bankrupt equals to true. Okay, and then we want to roll all the way up. For example, so this is a investment chart or the organization chart of companies, right? So this is the ultimate parent company, and these are its subsidiaries. And let's say this company is bankrupted, and as well as this guy and this guy, right? Then in this case, we need to maintain a set of vertices in order to traverse all the way up so that the parent company can get this info, right? So let's say this is company A, this is B, and this is C. Then we need to store them in the set along the way, right? So this guy has BC, and then this guy also has BC, and we pass away all the way up, and now it has ABC, something like this. We know that each vertex along the way need to maintain a set. So this will become very expensive, right? Because everyone carries a set with multiple elements. So in order to optimize this query, we can write it in the form of query calling queries, so that for each subquery, we only process the result for one company, like this, right? So here is where we define the subquery. It takes a vertex as the input, and these are the logic. These are the logic of this subquery, and this is the main query. And from the main query, you can see that we start from all the companies, and we call a subquery. Oh, sorry, we should have a accumulate clause right here, or post accumulate clause. Right. So in the post accumulate clause, we call this subquery. That means for each vertex in this vertex set, we'll call this subquery to get some result. And the input of this subquery is s. S is the alias of every vertex from this vertex set. Okay, that means I'm calling this subquery for all the companies and take the company ID as the input of this subquery. And from the subquery, I start from this ID. So you can see how it flows, right? And then starting from it, I traverse multiple hops and then print a number of subsidiaries that were bankrupt. Okay, so you can see in the subquery, all I have defined is an integer type count. So so by doing query calling query, we actually successfully reduced the memory consumption by using a local accumulator, set type accumulator to like a integer for one integer for each subquery, right? And even better, the subquery memory will get released every time we call it, and only a very limited amount of subquery can be run in parallel. Okay, so doing query calling query can significantly save the memory. However, it doesn't guarantee you have better performance. It's kind of like trade performance for memory. Okay. Okay, and the fourth technique is clear up the used containers. So when your query uses vertex attached container type accumulators, and the query traverses multiple hops and doesn't revisit the vertices, you can clear out the used containers to release the memory. And also this is mentioned when we talk about the first technique, right? So we can actually clear out the containers after once it is being used. Oh no, the second technique here, right? So just call this .clear function for unused containers. The system will release the memory for you. So that's the fourth technique. Okay, and that's all the content we have today. we talked about the memory composition of the TigerGraph system, what consumes the most memory in the query, and what are the semantics and the operations in the query that consumes more memory, and the techniques to mitigate this problem and to optimize the memory. Yeah.
Excellent. With that, let me remind everybody, you see the Q&A at the bottom. At the very bottom right-hand side of your Zoom panel. If you can click on that and submit your questions, we can answer those. I've got a couple of questions here, Shinyu. First one is about lightweight accumulators. So you mentioned that lightweight accumulator is a technique to reduce the memory usage. The question really is, does it offer equivalent functionality, same functionality as what would be otherwise possible with the regular accumulators, or are we changing the functionality or sacrificing the functionality for the sake of memory optimization for lightweight accumulators?
Right. So usually we need, usually it's kind of case by case. We need to look into this use case and see if it's possible to replace the heavyweight ones with lightweight ones, right? Sometimes it's possible and sometimes it's not. It's really case by case, right?
Got it. Excellent. And are there going to be, you shared the best practices here. Another question, you shared the best practices here about a lot about accumulators and about query calling query. Are those features available in other query languages? I mean, I mean, if you want to table that question and come back to it, that's fine. But that's like, is this available in GSQL only? Is it available in other query languages about accumulators as well as query calling query functionality?
As far as I know, it's not available in all languages, but especially for some pattern matching query languages, right?
Got it. So that's a unique feature of GSQL. I'll add a little more context around that. Additionally, we are currently involved in GQL. We are driving it actively with all of the industry players in graph database market to define the new graph query language. That's an ISO initiative. And we have submitted proposal for including accumulators. It may not show up in the first version of the GQL graph query language, but we are hoping that it certainly would be added in a follow-on version. And that's something that's an exciting development for the GQL community as well. And then I have additional information here from the product team on the accumulators. Accumulators are our own feature, query calling are our own feature, so that's not available with other query languages. Product management team just confirmed that. So it's not available in Cypher, for example, or with any other query language. Not available with Gremlin also. Query calling query is a SQL feature from the, as you will know, as you remember, GSQL is heavily influenced by SQL. So query calling query is an SQL feature that we have adopted to make it available in a graph query language. So those are the clarifications for the product management team for the questions. Again, if you have any other questions, feel free to ask them. I'm going to give it another moment, Shinyu, for people to ask any questions if they wanted to. Here's another question from the Q&A. Are you planning to provide any automated utilities in the future for checking for these coding best practices that you have covered in the three-part series so far? Shinyu, any plans from the solution team to provide any automated tooling or scripts and other things that will provide kind of?
I think this is also a question to our product team, as they are also here. So I think this is something like a query optimizer, right? I think ultimately we may have something like that in our system.
Okay, cool. So I will take that and take that back to the product management team, and they'll provide more clarity. Eventually, our plan would be to add query optimizer into the product, and we'll communicate the outcome of that. over a period of time. We are adding the memory management as a part of robustness improvement. So the product management team just got back in real time. We are adding that in as a part of the feature, as a part of the robustness improvement feature. We are already deployed at some of the largest graph deployments in the world. Tens of terabytes, but the idea is to keep on improving it with memory optimization that allows you to control the amount of memory that's allocated as another improvement in the future release. Okay, that's about the time we have today. Thanks a lot for joining us in. As I mentioned, we will send out the recording of this particular session to you for a replay if you could not join us live or if you want to go back and listen to it. Again, the way to reach you and I is simple, our first name at TigerGraph.com. And here is additional information for you on our developer forum, our community. Join the community. It has thousands of developers already engaged on it. We would welcome your participation as well. We have a developer chat at Discord. Join that. We also have every Thursday at 11 a.m. developer office hours. That's something that we will welcome you to join. Can we go to the next chart, Shinyu? We might have a preview for additional resources for TigerGraph. So here you have TigerGraph Cloud. Again, most of you are aware of this, but those of you who might be joining us for the first time, we have TigerGraph Cloud, our cloud edition available with the free tier. Feel free to join that and check out TigerGraph Cloud. We want you to experience the graph database and analytics, and we want to experience it with the most intuitive GUI possible, which is Graph Studio. Feel free to use that. Over 1,500 developers are already working on it, creating new applications every day. We would welcome you to join that crowd. We also have a test drive available. We have a developer edition for you to download in case you prefer to work on it on your own laptop as opposed to in the cloud. And last but not the least, we have all of the episodes where we have graph gurus with data sets and queries. Those are all stored in the Guru scripts on GitHub. So we contribute actively to all of the work that happens in open source. This is our way of contributing back all of the work that we are doing so that anybody can download it and use it with the developer edition or use it with the cloud free tier. And learn about graph database and analytics and build really cool applications like thousands of developers have been doing on cloud as well as on premise. Lastly, and the last chart, let's go to the next chart. We have two upcoming webinars that are coming up. Next Wednesday will be Graph Gurus 37, that's focused on an exciting topic, combining natural language processing or NLP with a graph database. And for example, we have taken a COVID-19 data set. You'll remember that White House announced an initiative around it and released the data set on Kaggle. As a result of that, we're going to show you how to use that along with an NLP tool, combine that with TigerGraph and work with Google Colab Python environment to create a unique solution. So join us next Wednesday at 11 a.m. for that. And last but not the least, one of our partners, Galvanize in the development community, is also hosting an online workshop on Friday, the June 5th. So depending on which one you can join in, please join us. And we would love to have you learn more about graph database and analytics. With that, I wish you all great rest of the day, and we'll see you back on next Wednesday for the Graph Gurus episode 37. Thank you.